Good morning, everybody. Let us slowly begin while our presenter is trying to connect. It is my pleasure to introduce Dr. Anil Fernando. Anil Fernando leads the video communications group at the University of Surrey, United Kingdom. He has been working in video coding and communications since 1998. This for 17 years now, and has published more than 270 international reference journal and proceeding papers in this area, including a book on video communications. Furthermore, he has published more than 150 international reference journal conference papers in multimedia communications. He has contributed to several international projects like Romeo, Muscade, Diomedes, Visnet, etc. And currently he is leading an interactive video communication project, Action TV, funded by the European Union on Media Communications. Recently, he has won the IEEE Chester Shell Award, sponsored by our Consumer Electronics IEEE Society, for one of his work in 3D video compression. And over the last 5 years, he has given numerous tutorials in at least 7 different ICC conferences.
Good morning, everybody. So my name is Anil Fernando. So here with me, I have also one of my colleagues, Thanuja Mallikarachchi from my lab. And we'll be talking about the basically the HEVC and its challenges for future and current wireless systems, and what's its impact for the quality of experience. Yeah, thank you. Quality of experience in general. So before I start, so I should thank to the ICCE management team for asking me to come here to Las Vegas to talk about these interesting topics and inviting us for this tutorial. Before I start about the presentation, so let me give you some introduction to my lab in Surrey. So this is called iLab Multimedia Communications Lab. So we are part of the Center for Vision's Speech and Signal Processing Center in University of Surrey, which is one of the largest research centers in Europe in signal processing. So basically it concentrates on in many aspects of multimedia, and here within the iLab we talk about consider mainly the multimedia communications. So we have about 40 plus researchers, and we are one of the key players in many of the European Union research funding projects. So these are our expertise and main research areas at the moment. We are mainly working on 2D, 3D video coding and processing, audio coding and processing, and quality of experience modeling, and use of QoE for different multimedia applications. And recently we started cloud communications and intelligent networking aspects of media transmission, and also multimedia communications in general. Since we are mainly working on European projects in multimedia communications research, so this is our main project at the moment, which is called Action TV project. And in this project, we are trying to relax the rigid nature of the present broadcasting ecosystem, where we only have a passive broadcasting environment. At the moment, users are kind of forced to experience what is broadcast from their TV channels. So here we are challenging that concept, and we are trying to introduce several aspects of interactions where the users can play their own parts with the broadcast content. They can interact with the content, and also they can interact with their social peers with the broadcast content. So to achieve that, we are working on novel content generation techniques, which facilitate the user interaction for broadcasting and media communication. And user model generation, we are developing like kind of 3D photorealistic modeling integrate the users to the broadcast content and rebroadcast to the social groups. And other than that, we are also working on resource optimization using cloud technology in order to happen this interaction with the broadcast content with their social peers. And also we are working on highly interactive content consumption, compression, as well as the social part of that within the project. So here is an example, how does it work, for example. So here we have the passive broadcast content. So what we are doing here is we are introducing some interactive points. At these interactive points, users, you will be invited to interact with the content either by doing some kind of interaction with the content, or they will be asked, they will be given different options based on that option, so the content can be changed for different users. For example, if you raise your hand, so the content will be changed to something else, and so on. So in this type of interaction, users can also be part of the content, where the users can be captured using the home system, which is quite similar to the Connect system, but it is more advanced than the Connect system. So the users will be captured, and these users will be represented by a 3D photorealistic model, and that model will be seamlessly integrated to the broadcast content and then played back to the users for different social groups. So this is the end-to-end system architecture. This is the main broadcast system, and whereas these are the auxiliary streams, we define these as auxiliary streams because these will be helped to the users to engage with the content according to their interaction with the content. And for example, here we have millions of social groups by the same broadcast content, and that will be facilitated by different auxiliary streams and within a social group. So this broadcast content will be consumed by different social groups according to their interactions, their colleagues' interactions, how they are interacted with the content, and so on. So this is a very high-level concept of this project, which was started a few months ago, sorry, not, about 12 months ago, and we are now merged into the year number 2. Hopefully there will be a demonstration in IBC this year or next year in Amsterdam, Netherlands. So apart from that, so this is the overview for the talk today. So we are talking about mainly on HEVC and its architecture and its problems and challenges in real video transmission in error-prone channels. And also we are talking about briefly about the quality assessment techniques, which is quite getting important now, especially the no reference quality matrices. Their use of the models which we can use for QoE estimation at the receiver side without the reference signal. So without that, we cannot take any decisions at the decoder, especially when the video is transmitted over an error-prone channel. So this is kind of an introduction to the video chain. I have selected here the 3D video as an example. So here we have the capturing happening at the transmission point. Then we have kind of post-processing techniques and the preparation of the content for the transmission. And we have different type of transmission channels, from satellite to mobile networks, wireless and broadband channels. And then at the receiver side, we have, if it is a 3D, we have synthesizing algorithms will be employed at the decoder, and then we have the display, and then the quality of experience is decided at the user's terminal. And why video coding is important? As you know now, video is considered as the main traffic in 2-3 years' time. The Cisco has predicted, for example, about 90% of the internet traffic will be based on video. And that will have a lot of challenges as video people, I mean, for compression and transmission and the maintenance of the quality. So that leads to this kind of a scenario here. We have this video compression and the multimedia technologies evolution. We have problems on production, and then we have post-processing algorithms, the storage, and then the distribution or the transmission of video, and then the complexity, and also energy is getting an important factor in few years' time, especially in ICT domain. To start with HEVC, I think I thought that we should have some kind of basic understanding about the video coding, why video, for those who are not working on video. So why video coding is needed, and the basic concepts of video coding before we start on HEVC. So as you know, video needs a very high data rate. The bandwidth is getting more congested, especially in wireless systems. So therefore, the per byte cost of transmission is very high. We have to go down to get it more attractive for any business modeling, especially which is involved with video. So what we are doing in video coding is we compress the video. It's a reversible conversion of data. I mean, of course, there is lossy compression and lossless compression. Depending on the applications, we have to consider several bitrate reduction, and which requires fewer number of bits, and then we have, at the end of the day, we can transmit the content with more efficient algorithms. Similar to the JPEG and JPEG 2000 for image compression, we have to use different algorithms for different standards for compressing the video. So unfortunately, this video cannot be played on this computer, so I can try it here. So this is one of the video that you can consider, like, this is the uncompressed video, but I think the compressed video is having problems here. Let me try. No, it is not compressing. The idea here is like we can have different quality of experience subjective tests to compare the quality of this compressed, uncompressed video against the compressed video. So the human visual system will not be able to judge any kind of noticeable distortions, but at the same time we can say that the bitrate can be reduced by approximately 100 times compared to the original video. Three types of redundancies we are considered in video compression algorithms: spatial correlations or spatial redundancies, which will exploit the correlation in the spatial domain. Since the adjacent pixels are highly correlated, we can exploit that in the spatial correlation with some spatial correlation algorithms like DCT or discrete cosine transform. The second redundancy is the temporal correlations. We have, when we move along with the time axis, the adjacent frames are highly correlated. That can be exploited using any temporal correlation algorithms like motion estimation. And finally, the human visual system. We can make use of the properties of the human visual system to understand some algorithms or develop some algorithms to exploit these HVS properties when compressing the video data. So if you consider the previous video coding standards like MPEG 1 and 2, they have considered different frame structures, intra-frame and interframes. Intra-frames are coded and encoded using the features within the same frame, and they do not get any information from the adjacent frames. Whereas in interframe compression, they consider adjacent frames, get some information from neighboring pictures to compress the frames in question. And this is a typical video encoder, which is still applicable for the coding standards like HEVC. And we have three main operations here: the motion estimation, which will capture the temporal correlation of the video, and DCT is discrete cosine transform, which will capture the spatial correlation, and we have the quantizer, which is the main function to control the quality of the video. So, for example, if we have an intra-frame, so discrete cosine transform is applied in blocks, and then the quantize, and then entropy coded and send it to the decoder. And if it is an interframe or the interframe, we have to do the motion estimation to calculate the motion vectors, and then we compensate the motion, and then take the difference between the original and the compensated frame, and the error signal is subjected to discrete cosine transform, then quantize and entropy coded and send it to the decoder together with the motion vector. So this is a typical video encoder. The current video coding standards like HEVC is a bit complicated compared to this one, but still the basic principles will not be changed. And at the decoding side, again, we have to do the motion compensation from the motion vectors which has been transmitted. And once you generate the motion compensated frame, and then we have the error signal, or if it is an intra-frame or inter-frame, and we generate the error, and then the motion compensated signal will be handled with the error signal which is generated from the decoder to reproduce the content. So we have 3 different picture types, or intra pictures, and then we have 2 predicted picture types, B pictures, and bidirectional predicted pictures and forward predicted pictures. And for example, in MPEG-2, this P picture is predicted from this I, and this P is predicted from this P, and B pictures are predicted bidirectionally from the previous reference frame I and future reference frame P. These same concepts are still used in HEVC. And the quantization is the process that attempts to determine which components is most sensitive to the human visual system and which components can be safely discarded without affecting the quality of the video. So this will be considered as the main function to control the bitrate against the quality. So depending on the quality, we can control the bitrate without any problem using a proper quantizer. So this is a typical structure of the complex video sequence. For example, it's MPEG 1 and 2. We have the sequence, the group of pictures. Set of pictures are assigned as the group of pictures. Each group of picture or GOP is subdivided into pictures, and picture is again subdivided into slice, and slice is subdivided into macro blocks, and then each macro block can be divided into blocks. So in the bitstream syntax, we have the sequence header, GOP header, and GOP information. Picture level, picture headers, slice headers, macro block headers, and so on. And then the next sequence, and so on. The same thing is still applicable in present days video coding standards. And if you go into more details about the iframe, this is again MPEG 1 and 2. Basically, a picture coded is coded without any reference to any pictures, adjacent pictures. So it's kind of an still image encoding technique like JPEG. And once you code this picture as an iframe, this can be used for the future references for following pictures. And this is again a simple explanation for the intra-coded pictures. We have the input video from RGB to YUV or any other formats, and subdivided into blocks, and each block is subjected to the discrete cosine transform. And then we have the discrete DCT coefficients here. All these coefficients are concentrated towards the low frequency end, whereas the high frequency frequencies can be removed without any problem using the quantization process. And then we use the zigzag scanning method and then run length coding and send it to the decoder. So this is the basic concept of intra-coding. And intercoding, we have to exploit the temporal correlation, which is the main function in interframe coding. So we do the motion estimation. We have a target frame, the reference frame, and then we have the reference frame, or the reference frame, and then we have the target frame, which is the frame which is encoding now. And when we encode this block, we define a search range in the previous reference frame or in the future reference frame, and depending on the search range, we find the best match for this block in the reference frame, and then we calculate the motion vector. The motion vector is calculated subjected to a certain criteria. If you use a mean square algorithm, for example, motion vectors are calculated such that we get the least amount of errors compared to the target and the reference block. So for example, here if you are finding the motion vector for this block from the reference frame, so this is where we search in the previous frame, and then based on that we find the best motion vector to represent this block. So if it is a P frame, bidirectional, forward predicted pictures, we will get as one motion vector set for each block, and then we have the predicted signal, and then the actual signal. We take the difference and then send the error signal to the decoder using, for example, using a Huffman code. And if it is a bidirectional predicted pictures, we have two sets of motion vectors and their corresponding error signal. And we take the average, for example, and then We have less energy error signal using a bidirectional predicted pictures because we have two sets of motion vectors which can exploit certain unknown information like occlusion information if we have two reference frames, and then we can further reduce the bit rate for the error signal. That is one of the reasons that we are using B frames. And this is, for example, again for MPEG, we have three picture types, I, P, and B. So this is one way of predicting the B pictures, bidirectional predicted pictures. And we can have any number of B pictures according to the standard from 0 to 3 or 4. So with that same concept, so high efficiency video coding is the latest video coding standard which has been introduced in 2003 and which is getting its momentum for different applications. So now I will hand over to my colleague Thanuja to talk about more precise details about HEVC.
Thank you. Before we move into further details of the high efficiency video coding, so we are trying to give you a basic introduction about the building blocks of the HEVC standard, and then we'll move on to some of the challenges that we have identified in the process of video compression and video transmission. So first of all, if we look at the main reasons why the novel coding standard is required, so as it was mentioned earlier, several indexes that forecast the networking aspects have predicted that in near future, most of the IP video traffic will be video data. And on the other hand, since the increasing penetration of mobile devices have paved way to exchange a lot of video data through mobile traffic. So these are some of the major reasons why a novel coding standard is required. And of course, if we look at even today's context, the consumer electronics show that is being held, we see that there's a huge demand and rapid growth in the 4K TV market. And several statistics have shown that the market penetration is increasing, and there's a huge demand for 4K compatible ultra-high definition content as well. In the meantime, the streaming solutions of such as Netflix, and even there were some novel innovative companies as well who have started the ultra-high definition content streaming, so that which is going to dominate most of the consumer networks in the near future. So these kind of requirements pave way to have a better compression standard than the ones that we have today. So with that in mind, the HEVC was introduced as the successor to H.264, which is the most predominant standard as of today. And it was standardized in early 2013, and it has some of the main design goals, which is targeted to compress HD and UHD content, and while improving the compression efficiency, and also providing some of the parallel processing features to utilize the parallel processing architectures that are available today for video encoding and decoding. If we look at the encoding architecture, it is a similar hybrid encoding architecture, but the the details or the compositions of these building blocks have been modified to a great extent in order to provide a higher compression gain compared to its predecessors. So if we briefly take a look at some of the architectural differences between H.264 and HEVC, we see that the major processing block has been expanded to be 64 by 64 pixels coding tree unit, and it has been estimated, or it has been proven that extending the major processing unit size have resulted in achieving higher compression gains for very high resolution video content. The coding architecture has been defined as a quad-tree flexible coding architecture comprising of coding units, prediction units, and also transform units, which is capable of providing a very high coding efficiency, which because it provides the capability to capture some of the pixel domain characteristics of the videos, as well as the transformed coefficient characteristics, so that the content can be compressed in a more efficient way. The intra-prediction has been modified to have 35 modes from 9, which is available in H.264. And the interprediction process has been modified to have to achieve the predicted motion vector using a motion vector competition scheme, which involves 2 modes such as merge mode, skip, and the advanced motion vector prediction. The transform process has been modified to have a similar transform process, but which involves larger transform block sizes extending from 4x4 to 32x32, and also it has a DST, discrete sign transform based process for smaller transform blocks. The interpolation process for motion compensation, when it comes to fractional Pell interpolation, it has been extended with more larger filters to achieve better interpolation techniques, so that the bitrate or the coding efficiency can be improved by using these extended filters. And the entropy coding process has been modified to a certain extent to achieve a high throughput than the previous CABAC implementation in H.264. And the in-loop filters have been, the deblocking filter is similar to what we had in H.264, but it has been modified to utilize the capabilities of parallel processing. And the sample adaptive offset filter has been introduced to provide to improve the reconstructed pixels after the prediction. If you look at some of the features that have been included in HEVC, and some of the features have not been included from the H.264, the FMO, flexible macro block ordering, and the redundant slices, the arbitrary slice ordering techniques, these have been removed from the HEVC due to the rare usage. But on the other hand, several new features have been introduced in HEVC, such as the video parameter sets, clean random access pictures, so that you can use them instead of the traditional IDR frames, and the broken link access pictures, you can utilize them to at stream switching points, and the temporal sublay access pictures, so that these can be utilized when the stream switching with the temporal scalability. Tiles and wavefront parallel processing, the slice segment architecture which includes dependent slices and independent slice segments, and also the reference picture set concept for the reference picture management in the decoded picture buffer. So similar to H.264, there's a network, the null unit concept, network abstraction layer concept is still there, but with the header informations have been changed. And the video coding null units contain the coded sample data, and the non-VCL null units contain metadata such as the parameter sets. The null unit header has been extended to have 2 bytes length, which has the null unit type in the these 6 bits, and there are some reserved bits available for the scalability extensions, which will be utilized in the HEVC version 2, which is coming up. And also the temporal scalability indicators have been located with these last 3 bits. So the architecture of this null unit header is expected to be mainly utilized by the network elements such as media-aware networking elements, so that intelligent media-aware streaming adaptations can be utilized to support the network contents and other resource constraints, as well as the device capabilities. For example, in terms of the scalable video coding, so the temporal layer bits available in the null unit header can be utilized by the middle elements, the media gateway elements available that could be placed within the network, so that these separate devices can be provided with different bit streams by dropping certain frames based on the temporal layer information. So this kind of architecture is possible with these new syntax elements that have been introduced. So the parameter sets concept has been introduced in H.264 as well to reduce the effects of losing header information at the decoder side. The video parameter sets are utilized to store the layer information that are applicable to multiple layers. Sequence parameter set has been utilized to include information related to all the slices, and picture parameter set to store the information related to individual pictures. So the relationship between these parameter sets can be expressed as the slice header will point to the related picture parameter set, and it will be pointed to the sequence parameter, and then it will be directed to the video parameter set. The picture types that are available can be categorized into the random access point pictures, the IDR instantaneous decoding refresh pictures, which are traditionally being used for the random access. The new types are the broken link access and clean random access. The clean random access picture is capable of improving the coding efficiency while providing the random access capabilities as well, because in the next slide we'll discuss how that will take place. And the leading pictures are, there are two types, the random access decodable leading pictures and random access skipped leading pictures, and also the temporal sublayer access pictures. So if we look at how the IDR and the clean random access pictures are capable of providing the random access. So if the I-28 picture is considered to be an IDR frame, the B30 will not be able to be decoded, because if the random access starts at this point, the previously decoded pictures will not be available. P24, for example, will not be available for the for B30 to reconstruct B30. With the CRA pictures being introduced, the P24 will also be available unless the random access doesn't happen in I-28. B30 will also be able to decode because the P24 will be available. But if the random access starts at I-28 picture, only B29 and B30 will be able to decode. And these leading pictures, these leading pictures can be categorized as these two as the RADL, the decodable leading pictures, and B30 as the skipped leading picture, because this will be discarded when the random access happens at I-28. So this process basically improves the coding efficiency while being able to provide random access capabilities as well. The reference parameter, the reference picture set concept has been introduced to manage the status of the decoded picture buffer. There are the fundamental difference between what is available in H.264 and HEVC is that H.264, the relative changes to the decoded picture buffer are signaled, while in HEVC, for each and every slice, a complete set of reference pictures that must be used for the current picture or the pictures that are coming in subsequent or in future are also signaled in the slice. So in this way, information from the earlier pictures are not needed to manage the decoded picture buffer, which is much more easier and convenient in the case of managing the decoded picture buffer. So it is being, this can be configured in the configuration profile provided with the HEVC. So these set of information can be utilized to manage the decoded picture buffer when the interprediction is being taken care of. And if we look at how this works, in this set of pictures that are being provided, when P1 picture is being, with P1 picture, the RPS is signaled to maintain I0, which will be used for future decodable pictures, B2, B3, and B4 as well. With B2 being transmitted, the decoded picture buffer is signaled to maintain I0 and P1. And both of these will be utilized for predicting B2. With B3, the RPS signals to maintain I0, P1, and B2 in the decoded picture buffer. Even though B3 doesn't require P1 for the prediction process, but it is being required by a future frame. So P1 is also signaled with B3 to maintain within the decoded picture buffer. With B4, P1 and B2 are being signaled, so the rest of the frames will be discarded from the decoded picture buffer. If we look at the flexible quadria block partitioning structure in HEVC, so this is a typical video frame where several partitioning structures are visible, and it is capable of capturing certain spatial temporal characteristics of a video frame, such as slow motion as well as very high motion characteristics. The coding tree unit, which is the main processing block, is a 64 by 64 block, and it consists of coding unit, which is one of the major blocks which maintain whether it is inter-predicted or intra-predicted. Then we have the prediction units, which reside within a coding block, which can have multiple prediction modes. And also the transform units, another transform tree structure, which goes from 4 by 4 to 32 by 32 to maintain the transform information. Then a frame can be partitioned into slices, similar to what we have in H.264, and then in HEVC there's a concept of slice segments, which are grouped into two more parts, dependent and independent slice segments, and also tiles. A frame can be partitioned into one or more tiles so that each tile can be processed by a separate processing unit, and it has been introduced to partition the picture to improve the parallel processing capabilities. If we look at the modifications in intra-prediction, so there are two prediction unit modes. They are 2n by 2n and n by n. The n by n PU size is restricted to 8 by 8 CU size, which is the smallest coding unit size available in the standard. And we have 35 prediction modes, 33 angular predictions, and DC and planar prediction. In the DC mode, the prediction is carried out by calculating the average value from the above or left prediction units that are available, and if none of these are available, the bit depth is being used. The mid value of the available bit depth is used as the DC prediction value. For planar mode in HEVC, and the average of two linear predictions have been utilized. And in angular mode, the prediction of integer positions is directly replacing the reference sample available for that position. But when the position comes to a fractional sample, a 1 over 32nd position of precision has been utilized to calculate the predicted value. In angular prediction, each block is predicted from spatially neighboring samples. For a block of n by n, 4n plus 1 samples are required. So for the ease of implementation within the encoder, all the samples are projected to a single row or column depending on the direction. For example, the reference samples which are located in this part of the left column are projected to the top row so that they can be processed in an easier way. So there are three cases where no reference samples are available, and all the reference samples are available for the block, the top row, top right, left, and left bottom. And when the reference samples are partially available, when, for example, when the left bottom section is no longer available, the reference sample that is available in the last position of the column are repeated to generate the available the reference samples. The reference sample smoothing techniques are being carried out to using a 3-step filter, which is a novel feature introduced in HEVC, and boundary value smoothing has been introduced to avoid the discontinuities at the block boundaries. And due to the increasing of the prediction unit modes, a most probable mode coding mechanism has been introduced with HEVC to improve the coding process. And also the mode-dependent coefficient scanning has been introduced for smaller block sizes, and which is also another feature in intra-prediction. If you look at inter-prediction capabilities, the three modes, merge mode, skip mode is also considered as a variant of the merge mode, and advanced motion vector prediction, which is the motion vector prediction mechanism, has been introduced. For merge mode, for motion, the neighboring blocks, motion vectors of the neighboring blocks is utilized to generate the motion vector, and the temporal candidate is being used by C3 position and H. And a motion vector competition scheme is introduced to derive the candidate so that a particular motion vector is used as the predicted motion vector in the case of AMVP. In terms of the fractional Pell interpolation, so these are the filter coefficients which are being used for 8-step and 7-step filter, and for chroma, 4-step filter is being introduced. So as the motion parameters, we have the motion vectors, the reference picture index, and the prediction direction. And the chroma motion vectors are derived from Luma motion vector, and the same reference picture as well as the prediction direction is being used. And the block matching algorithm is used to find the motion vector. So first, the integer Pell motion vector is being carried out, and the half Pell motion vector is then generated using the best found position motion vector of within the integer Pell MV, and then followed by the quarter Pell motion vector prediction. So the motion search strategy is being carried out as follows. The starting position is being utilized by the motion vector predicted positions, then the first search and the refinement search. The search process has been carried out using a diamond search pattern or the square search pattern, which you can configure within the configuration file. Then the transform quantization and entropy coding mechanism. So the residual which comes from the predicted and the original is being transformed using the transform coefficients, the transform matrices, and the transform coefficients are then quantized, and then the quantized coefficients are entropy coded and generated, bit stream is generated. So the reverse process is being carried out at the encoder side. So in HEVC, the finite precision approximation of the DCT matrix is being utilized for the generation of transform matrices, and the separable property of the transform matrices is being utilized to carry out the transforms using 1D transform, endpoint 1D transform for each row and column separately. So in HEVC we have transform sizes 4x4 to 32x32. An exceptional case is to have the DST for 4x4 intra-predicted residuals. So these are the transform matrices that are being used in HEVC, and the encoder description, the references that are available, so more details can be are available in these references. So as mentioned, the 2D transform is carried out as 1D column and then 1D row transforms. And due to the integer approximation, there are some scaling factors that have been introduced. And after the scaling factors have been provided, the quantization is being carried out with the generated Q step. And the scaling factors are being introduced in such a way that the properties of the DCT are being retained after the transform, which is lost due to the finite precision approximation. The entropic order is composed of several main building blocks. So this gives a brief idea about the main building blocks that are available. So there's a binarizer, which is used to generate a bin string. This is combinations of certain binarization technologies starting from unary to Coulomb-Rice codes and exponential Coulomb-Rice codes are being utilized here to encode and generate the bit stream. The in-loop filtering process is carried out at the decoder after decoding the null unit. Then the deblocking filter is applied, followed by the sample adaptive offset filter. Deblocking filter is applied to the samples at the block boundaries, whereas the sample adaptive offset filter is calculated as offsets, and these offsets are added to each and every sample to improve the reconstruction accuracy of the block. If you look at the deblocking filter, the blocking artifacts are being reduced by applying the deblocking filter, and in HEVC it is being carried out at 4 sample strength lengths on 8 by 8 sample grid. And there are several filtering criteria to decide whether the deblocking filter should be applied, because in human visual system it has been found that when the two sides of an edge are relatively smooth, the blocking artifacts are more visible. So in order to, before applying the deblocking filter, several conditions are being checked whether the blocking filter has to be applied or not. So there are some 3 criteria. The boundary of the block should be a prediction unit or a transform unit boundary, and the boundary strength, which is calculated in a different process, should be greater than or equal to 0, and the variation of signal on both sides of the boundary should be less than a threshold. For Luma, the filtering process is being carried out only when the boundary strength is greater than or equal to 1. For Chroma, it is being carried out when the boundary strength is equal to 2. This flowchart gives a basic idea about how the boundary strength is calculated, assuming that P and Q blocks, which are mentioned here, are 2 adjacent blocks. And these conditions are being checked to determine what the boundary value is. So these are some of the conditions that are being checked to verify whether the boundary, whether to carry out the deblocking filter or not. Sample adaptive offset filter is a process that classifies pixels within a block into several categories, and it attempts to reduce the distortion by adding an offset to these categories. So the blocks are categorized into 5, and the edge offset contains these 4 SAO types, and there's another band offset, and each SAO type has 4 different categories. And the edge offset is being carried out and this is the condition for each and every category of the edge offset. And the band offset is also carried out in a similar way. And the idea is that the offset that is being calculated within the encoder is passed on to the decoder, and after the reconstruction process, this offset is being added to each and every pixel which falls into the selected category, so that the further distortions will be reduced. And in terms of parallel processing, the frame level and slice level and macro block level parallelization technologies that are utilized in H.264 have some drawbacks in their own way. and HEVC attempts to introduce parallelization in terms of tiles and wavefront parallel processing, which is far more efficient in terms of the coding losses that are being introduced in H.264 when the frame is divided into certain slices. In terms of tiles, the frame is divided into rectangular blocks, and similar to slice breaks, the tiles also break the prediction dependencies, which causes the compression losses. And compared to slices, there's a possibility with tiles that the picture can be partitioned into sections with high correlations, so which is not possible with slice, but tiles are capable of doing that. But the RD losses are also present, which is because the dependency breaks are still available with tiles, and the resetting of Quebec probabilities also reduces the coding efficiency. In wavefront parallel processing, a CTB row is considered as a separate partition, and there is no dependency breaks between the rows, and therefore the RD losses that are visible in the tiles or slices is pretty much low in the case of wavefront parallel processing. So it allows the processes up to number of CTB rows can work in parallel. So if you look at the differences between WPP and tiles, the high number of partitions with low coding losses, but in contrast to the tiles where the coding losses are eminent, and with the increase of number of tiles, the coding losses increase, and it has been shown that the square tile shapes have less coding losses than row tile shapes. WPP is considered to be much more efficient in low delay applications when it is combined with wavefront parallel processing and slice segments, whereas tiles are much more efficient in terms of region of interest coding. And the limitation of WPP is considered as the parallelization is fixed to the number of CTB rows that are available within the picture, and the encoder can, with respect to tiles, the encoder can adjust the number of tiles for the available computing resources. So in terms of the challenges of wavefront parallel processing and tiles, we can be seen that removing the parallelization limitation, which is the fixed number of CTB rows, is one of the challenging research area, and also choosing the number of correct partitions in terms of tiles that minimizes the rate distortion losses as well as the region of interest requirements is also one of the key challenging areas that has been identified. So the HEVC is considered to provide a 50% bitrate reduction compared to H.264 and AVC, and these are some of the results that we have achieved when comparing HEVC with H.264 JM 18.5, and clear significant coding gain is visible in these graphs. And even though the HEVC provide a significant coding gain, it has been provided that the encoding complexity is much severe in HEVC due to the complex encoding algorithms and the increased the flexible coding architecture, especially the flexible coding architecture, and the rate distortion optimization techniques that are being carried out to determine the best coding modes and coding architecture are some of the key challenges that needs to be addressed. With this, it brings us to some of the challenges that we see in terms of in HEVC for the video communication. As mentioned in the previous slide, the complexity of the encoders and decoders is one of the key challenges. There are some optimized encoders available in the market in open source as open source softwares, but it has been shown that the speed ups of the encoders and decoders are being introduced by the extreme parallelization techniques, and also by sacrificing the rate distortion efficiency. So the complexity of the encoders is a challenging area because the techniques have to be defined in such a way that the fast encoding capabilities should be provided while maintaining the rate distortion efficiency, which is visible in the when all the encoding features are available. Another challenge is the limited energy in mobile devices. So the penetration of mobile devices and the usage patterns of users in exchanging video content over mobile devices has introduced a great deal of challenges in terms of the energy efficiency of the encoders and decoders. And also the error resiliency and concealment in video transmission, scalable video coding and adaptive streaming, which techniques that needs to be used, and also the futuristic user interactive applications such as Action TV provide some new challenges in terms of the video coding, and also the high dynamic range and 3D video coding are some of the new challenging areas which are upcoming, and there's a great potential for new researchers in these areas. So if you look at the complexity reduction, the complexity of the rate distortion process is one of the key challenging areas with the increased number of coding modes and the flexible coding architecture. The rate distortion cost function, which is mentioned here, where a set of coding modes or decisions which are available from a larger set of coding modes and decisions. The encoder tries to detect this P from PK, which minimizes the distortion as well as minimizes the rate. So evaluating this cost function for all the coding modes that are available is one of the challenging tasks. And in terms of research, in recent years, we can find numerous works that has been published which try to reduce the number of coding modes that are available, that are evaluated with using for the cost function, is one of the major researchers that have been carried out. And also the early determination of coding structure and modes, which skips the evaluation of the cost function, is also another branch of complexity reduction. And also, as described earlier, the sample adaptive offset parameter determination is one of the other complex tasks to determine the optimum offset, which reduces the distortion. That's also another complexity reduction that needs to be carried out within the encoder. And in terms of the motion estimation, the search range limitation and also the optimized motion estimation techniques are some of the other challenging areas. And also the evaluation of parallel processing tools. For example, partitioning the frame to tiles and slices will reduce the coding efficiency because of the dependency breaks. So in order to achieve a parallel processing architecture which maintains the rate distortion efficiency is a key challenging area in terms of video coding and HEVC. If we look at the energy efficient encoding, the adaptation of power rate distortion models that are available for the previous standard is a key criteria when it comes to HEVC, because none of these power rate distortion models are, adapted to the new novel modes and the capabilities of new standards such as HEVC or even H.264. The energy efficient dynamic encoder configuration is another branch that needs to be considered. For example, there are several work that has been carried out to dynamically change the coding unit sizes, coding unit depth, and also the number of reference frames, and also QP, depending on the energy requirements. There are some solutions that are available that utilize MPEG- technologies, which which uses the stream segmentations and also provide these segmented video clips based on the energy availability of the mobile devices. Normally, the MPEG- works as depending on the bandwidth requirement, but these type of new research areas have been introduced where the energy also considered as a parameter for requesting several video segments. And also the dynamic voltage and frequency scaling techniques for encoder and decoder solutions are also some of the emerging areas in terms of energy efficient coding techniques. Error resiliency and concealment is something that that has been overlooked in the HEVC standard, and the introduction of slice segments within the HEVC is capable of improving the coding efficiency while maintaining the maximum transport block size requirements. But the slice segments reduces their resilience capabilities due to the dependencies. So this is an area that needs to be investigated further, how to utilize these features to provide proper error resiliency and concealment techniques. And also the utilization of temporal motion vectors is another dependency which needs to be controlled in an efficient way so that the intelligent use of temporal motion vectors can be utilized to reduce the dependency and improve the error resiliency. And also in terms of efficient selection of coding parameters to reduce error propagation in error-prone channels, while also maintaining the rate distortion performance is another key challenging area in terms of HEVC. There are some other researches available for tiles and slicers to utilize these features to provide effective error resilience. And also there are ways of providing utilization of temporal scalability features and SCI messages for error detection and concealment within HEVC. So error concealment-aware encoding techniques, as mentioned earlier, are some of the prominent areas that needs to be addressed when it comes to transmitting very high resolution content encoded using HEVC in an error-prone channel. As mentioned earlier, the adaptive streaming using main media-aware network elements is something that can be considered with the adaptive streaming services such as MPEG-. And it has been identified that using scalable video coding techniques and performing adaptive streaming services using media-aware network elements offers more flexibility and than MPEG- solutions. But both these technologies should be able to be utilized in order to provide more efficient adaptive streaming solutions. And when it comes to interactive applications such as Action TV, provides even more challenges for the video coding side, where the interactive applications, as envisioned in the near future, are in terms of a way of integrating user models to pre-produce broadcast streams and mixing the intermediate content at nodes such as cloudlets, which are more closer to users, and then rebroadcast them to several social groups. So the generation of multiple personalized streams at local cloudlets for co-located social groups is one of the challenging areas. And this imposes certain encoding challenges, such as one is the real-time encoding capabilities and real-time rendering and content mixing, and also multiple transcoding cycles per user group, which will end up in quality losses as well as consume a lot of computing resources as well as encoding time. So the interactive applications, one of the key requirements in interactive applications is to maintain the real-time capabilities as well as the immersive user experience, which also indirectly and directly related to the quality of the content. So the multiple transcoding cycles at individual cloudlets, local cloudlets for individual social groups to generate personalized streams obviously needs to be controlled so that multiple transcoding cycles can be reduced, as well as real-time encoding capabilities are maintained. So these challenges require efficient real-time encoding solutions, as well as generating of coded bit streams, so that the content mixing can be supported within the bit stream, so that multiple transcoding cycles can be reduced. So with that, I will again hand over to my colleague to continue with the presentation. Thank you.
Thank you. So this comes to me to compare the performance against the previous video calling standards, the HEVC and H.264 and H.263 and so on. And as he mentioned before, so the coding gain has been significantly improved compared to the previous coding standard at the expense of the computational complexity. And people have, I mean, going beyond what we are discussing here, I mean, people have now coming up with several ideas for enhancing the complexity reduction in HEVC, and for that providing a pathway to have a real-time HEVC codec for different applications. So I think we also have a presentation maybe on Sunday for reducing the computational complexity in HEVC. So with that, we'll come back to the challenges in video transmission. As he mentioned before, like the real-time video communication is becoming a problem, especially with error-prone channels like LTE advanced channels and the future mobile systems like 5G. So the main problem is the way the more and more we compress the video data, and if there is any single bit error which happen during the transmission, or one packet drop may generate a lot of errors, and subsequently the future frames will also be affected, and so on, leading a very poor quality at the receiving side. So there are two techniques we can use in any data transmission techniques: the retransmission request and error residence or forward error control technique. So for real-time video communication, FEC is the only option that we can use, but again, we have to allocate more bits or resources for protecting the data, which will increase the bit rate. And coming back to the error residence tools and concealment, so these are the only one way of handling these problems. At the moment, mostly the encoder and the decoder are doing their jobs independently. There is no communication between the encoder and decoder, especially with calling standard like HEVC, where the data is more compressed, and we should come up with some ideas how to engage the decoder and the encoder in a more meaningful way to exchange the information, and then based on that, so encoding is done more intelligently to support decoding, and vice versa. So this is one way of looking at this problem. So we have also been working on this area at the moment. So there's nice, interesting results are coming up in few months' time, especially in a few next international conferences. So due to the time restrictions, so I'm going to exclude some of these slides. So data losses associated with bit errors or packet errors occur in wireless video transmission. I mean, can be handled in different ways. For example, here the data losses can be classified into different areas depending on their importance for the final video quality. For example, less significant information and prediction information such as motion vectors, and prediction loss due to synchronization losses, and loss of the entire frame. I mean, depending on these type of losses, we have to come up with some ideas how to deal with these different kind of data losses. So there are some error resistance tools which are already available in the literature, has been discussed widely with reference to the other video coding standards, localization techniques, disk data partition techniques like the one was introduced in H.264 AVC, and redundant calling techniques, concealment-driven calling techniques, and so on. And also the forward error correction codes can also be used, has been used in the past, and is being used in now with the HEVC as well, like Reed-Solomon codes, turbo codes, and LDPC codes in wireless video transmission. And just to give you a simple idea about how important the information is classified in HEVC compared against the wireless video transmission like LTE Advanced, here we have done some little experiments. And what we have done here is the whole frame is divided into different slices, and slices are ranked based on how important they are for motion estimation and compensation. For example, here, and this frame has been hypothetically divided into four different slices, and each slice has been ranked based on the motion vectors which has been referred to these slices. So, for example, these four slices now have been ranked. Slice 4 maybe is the top rank, 2 may be the next, and 3 may be the next, and the least significant slice is the slice number 1, for example. And depending on this slice importance, so we can allocate the resources in the wireless side in the base station. When we allocate the resource elements, so REs in LTE Advanced transmission, and in the resource grid, one data symbol is here, is mapped into the one resource element, and each research element is associated with one time or frequency instance, and robustness of each RE to noise or fading varies from different for each other. So what we have done is we have ranked again resource elements in the LTE radio frame based on their robustness, and then the more important slices have been mapped to the most robust resource elements, and whereas the least significant slices have been mapped to the lower order of the resource elements. And just by looking at so before that, so this is how we tested the performance. We have the original video, and then we rank the slices, and then we have the resource grid filling technique with the LTE Advanced transmitter. And ranking information, these are very little information compared to the compressed video data, which is considered as a metadata to the compressed data. And based on this ranking information, we allocate the resource elements in the grid filling stage according to the slice ranking. And then channel estimation is done with the user to rank the resource elements. And then we transmit the signal to the multipath fading channel. And at the receiving side, and we extract the data, and then decoded frames are decoded. Sorry, frames are decoded, and then compare the video quality against the original video. And these are the system parameters we use for this simple experiment, and you can see the performance improvement that we get out of this for different 3 video sequences. And for example, here for the highway sequence, and you can see that performance has been increased quite significantly, up to like about 30 dB gain at low SNR compared to the conventional video transmission. So things like that, I mean, this can be done quite easily, and of course, this is just one example. I mean, we have to somehow coordinate the network and the encoder and the receiver. And if you can coordinate these 3 units more intelligently, even with HEVC, you can get a very good video quality at the receiving side. In order to achieve this is one of the problems here. For example, here we assume that the decoder is having the knowledge about the original video. So we basically, at the moment, everybody is assuming that the input video is available at the receiving side to compare the video quality, because the decoder has to take its own decisions irrespective of what is happening at the encoding side. So the decoder doesn't know what is the exact information which was transmitted from the encoder. So therefore, there kind of a non-reference video quality metric should be available at the decoder to predict the video quality, and then based on that, with some side information from the encoder to come up with some intelligent decisions at the decoding stage. So that leads to a very important topic in video quality assessments, especially the no reference or reduced reference video quality matrices. Ideally, we should have a no reference video quality metric, because that doesn't need any extra information from the encoding side, especially for applications like 4K video and HDR video. Still, the bitrate is, we are talking about, even with LTE Advanced, we are talking about 15 megabits per second data rate, which is very high. I mean, to accommodate more bits on this will be quite overloaded to the network. So these are some of the reasons. I mean, video quality assessment has been there for many years now. People are talking about the quality of experience, and especially with 3D video and other types of video. And here I have included some of the information for the importance of having a non-reference metric at the decoding side to decide the quality of the video without any information from the encoder, without any additional information from the encoder. If we have this kind of model, and that model can be used down in the end-to-end system, for example, at the networking level, it can take intelligent decisions whether the content has been corrupted or not, how that affect to the final quality of the video for different users. Like he explained before, I mean, if the video quality is being predicted to be very poor at the receiving end, so then he can take some transcoding decisions to enhance the further robustness to the video and so on. These intelligent decisions can be taken down the line of the transmission system, and which will lead to a better way of managing this 3Q network, a 3Q system like quality of service, quality of experience, and the quality of business. All these three are linked together. I mean, if the quality of service is better, then the quality of experience is better. If the quality of experience is better, then the consumers are more satisfied, and which will lead to higher QOB or quality of business, which will generate more income to the network service providers and the content and the application providers. So I'm not going to discuss in detail about these quality assessment techniques, which has been there for many years now. I mean, obviously the objective matrices have been used like PSNR, SSIM, and VQM. I mean, there were some problems with PSNR. People are now replacing the PSNR with some other intelligent matrices like VQM, which are more correlated to the subjective test. And subjective tests are very expensive, but somehow we need to use some kind of objective matrices for different applications. And there are some advantages and disadvantages between the subjective and objective test. So I'm not going to discuss all these, but this is the most important part, the classification of quality matrices. Most of the quality matrices which are available at the moment are either full reference matrix or reduced reference matrix. What this means is, so in full reference matrix, so we have to have some knowledge about the input signal, and we compare the input and the output signal, and then we come up with a metric like PSNR. Each needs the input and the output signal for taking its decision. So practically, this is not kind of important for video transmission, especially, for example, in a wireless system where when the information is lost, so then the decoder is kind of clueless what to do. I mean, this is not an intelligent process. But for example, at the encoding level, so this full reference metric can be used to minimize the R&D cost. And the reduced reference, what it does is, so it kind of extracts some features from the input signal, and without having this full access to the original information, what it does is this set of features are transmitted to the decoder, and the decoder can make use of these features together with the output video, and then come up with some matrices to evaluate the quality. So video quality metric, or VQM, is one of that. So where it generates 7 different set of information which are transmitted to the receiving side, which needs about 10% of the payload of the data. And the most importantly, the no reference metric, which is the most ideal situation, if we can develop such a metric, more accurate metric which has a very high correlation with the subjective test, and such a metric can be very useful for video transmission. So people have been trying with some features like blockiness and blur can be used for modeling a no reference quality metric. So if still we are at a very early stage of the research, but if somehow we can develop such a metric without any information from the encoder side, which can be very useful for video transmission applications, which will kind of revolutionize the way we consume the video today. So these are some of the techniques that we are people have been proposed, and some of the work we have also been doing in quality of experience modeling for different video applications, and all this information are here. And if you need any more information, you can email me there so that I can send more information about these techniques. So this is a comparison between the 3 common matrices that we are using at the moment in the video coding research domain. They are objective matrices PSNR, SSIM, and VQM, and PSNR is very poor. Is very poorly correlated with the subjective test, but it's very simple. All the encoders can make use of these PSNR matrices very easily without any problem. But the encoding algorithms like HEVC, now if you use PSNR, the computational complexity that he was talking about, it uses PSNR for the RD optimization process. But algorithms like VQM, you can see that it's very complex compared to PSNR, but it's, the correlation performance with the subjective test is fairly improved compared to the PSNR. So that we can argue that VQM is much better than PSNR in representing the views from the users. So with that, so these are some of the algorithms that you can use for reduced reference frames. So these are some of the subjective evaluation criteria that you can use for any verification of the objective models that anybody is proposing. And out of this, double stimulus continuous quality scale has been very popular to validate the objective test. So there what we are doing is videos are played in pairs. Both videos are shown simultaneously. Each pair is repeated a given number of times, and one of the video is reference. The other one is the distorted one. So users will be asked to rank the quality of this video based on the chart, which is something like this. The reference video and the process video, we have to rank the quality of the video using a simple chart like this. And based on the results, we can evaluate the correlation. And this is some of the ITU standard which defines how the test should be done with different time intervals. For example, here T1 has to be at least 10 seconds, and between the T1 and T3, we have to have at least 3 seconds between the sequences, and so on. And all this has been properly explained in BT 500 standard. And the number of users are also defined, like if the users are experts in videos, at least 7 users can be used. If they are not video experts, then 15 users must be used for the experiments. And all these kind of simple definitions or requirements have been specified in BT 500. A logistic function like this has been used to map the results to calculate the correlation coefficient with the subjective results and the objective results. With that, I will come to the summary of the presentation. The HEVC standard is the latest video calling standard. We have been discussing quite significantly about the HEVC development up to now, and there are challenges for the future and the current video transmission problems. And beyond the transmission, and he also talked about the challenges we have for interactive video applications, which is the next generation of video industry. And challenges on video transmission in mobile networks is another problem that everybody will face in few years' time, how to optimize the resources, especially in 5G and the systems like HDR and ultra-high definition video transmission. Error resilience and concealment, so we have to think about new ways of generating error resilience and concealment techniques for future video communication systems. And the quality of experience is another area that everybody needs to look at, especially for non-reference quality matrices for video transmission applications. So with that, I conclude the presentation, and we have a few minutes for the questions, if you have any questions. Thank you very much.